So we have already derived three flux equations, right? So let me copy all of them here, and then we will discuss how to find a solution for the problem. So this is the volume flux balance equation. This one is the momentum flux balance equation. And this, which we recently derived, is the buoyancy flux balance equation. And for this one, okay. So let me just change the color so that we can clearly see these three equations separately. All right, so we have these three equations, and you can see there are three unknowns, that is R, W, and G prime, which are changing with Z. And there is just one axis, that is Z. So we can easily solve this equation by using a boundary condition. So to be able to solve it, we will first convert this into a dimensionless problem. And that we do because it makes our problem easier, and then that will be applied to any plume in stratified medium rather than a specific plume with given condition. Okay, so we start with dimensionless model. So we will first define characteristic length scale, characteristic velocity scale, and characteristic reduced gravity. Okay, and we will name them as L, capital U, and capital G. Okay, so let's see how we can find characteristic length scale or velocity scale or reduced gravity for the given set of equations. So we know that for the given plume, which is basically rising up, we have B naught, which is actually Q naught times G prime naught, where G prime naught is rho A minus rho naught divided by rho infinity, where rho A here is rho A at Z equal to 0. All right, so that is the G prime naught, which is also multiplied with G. So B naught is a known quantity, and also we know the N value, or to be precise, N square. Okay, so constants, known constants are B naught and N, right? Because B naught is the input buoyancy flux, is the source buoyancy flux, and N is the stratification frequency, and N depends only on the rho ambient, as we have already defined N square as minus 1 by rho infinity, which is G by rho infinity d rho A by dz. So you can see that it depends on rho ambient and rho infinity, and we already, for a given stratified medium, N square is constant, right? For a given stratified medium, N square is constant. Okay, and B naught, that is the source buoyancy flux, that is also constant for a given plume. All right, and what is the dimension of B naught? If you remember, this is m to the power 4 by s to the power 3. And what is the dimension of n? That is 1 by second. Okay, so this is something we have already derived in previous lectures. So now we are trying to define characteristic length scale, velocity scale, and reduced gravity, these three parameters, and we can do so only by considering the known quantities. Okay, so that is how your characteristic length, velocity, etc. are defined. And that is why we can actually start with characteristic length scale here. So for L, we all know that the unit of L must be meter. Okay, and we can use, here we are using only B naught and N. So to be able to get B naught and meter from B naught and N, we must divide B naught by N cube. So that will cancel the S cube from B naught, right? And now B naught has m to the power 4. So we do 1 by 4. So this actually gives us a unit of meter. Okay, so if you want to see how it's happening, B naught is meter to the power 4 s cube, and if you multiply B naught with, or divide that by n cube, it becomes m to the power 4 s cube divided by 1 by s cube, and that is why this one cancels out. So that becomes m to the power 4. Okay, and now if you want to get the dimension of meter, then you must put an exponent of 1 by 4 on this bracket, right? Then only it will become meter. So we define length scale as B naught over n cube to the power 1 by 4. Okay, likewise we can define the velocity. Velocity, the unit for velocity we know is meter per second. So now we will do that. We want meter per second, so we will again use B naught and N here, which are known quantity. So B naught is m to the power 4 by second cube, and N is 1 over s. So to be able to get m by s, we must first equate m to the power 4 by s to the power 4, right? So we should have the same power. And to be able to do that, what we can do is B naught over N. Okay, so B naught actually gives you meter to the power second cube, and S gives you 1 over S. So that becomes m to the power 4, S to the power 4. Okay, so that is B naught by S, but now we also need to divide it by 1 by 4 to be able to get meter per second. So what we will do, we will put an exponent of 1 by 4. So that gives us a unit of meter by second. Okay, and that is why we have defined our characteristic length scale, velocity scale as B naught by N 1 over 4. I guess there is a small mistake here. All right, my apologies. This should not be over n, because that will cancel s cube. It should rather be multiplied. Okay, so we'll do this process again very quickly. Okay, let me very quickly repeat this process. B naught n. So B naught n will b naught n gives us m to the power 4 s cube 1 over s, so that becomes m to the power 4 s to the power 4, and then b naught n to the power 1 by 4 will give us 1 by meter by second, and that is why we need to put 1 by 4 here. Okay, so that gives us meter over second, and that is why the velocity scale, characteristic velocity scale, is defined as b naught n to the power 1 by 4. Okay, so this is characteristic velocity scale. Characteristic length scale we already defined, and now we will define characteristic reduced gravity, and we already know that reduced gravity has the unit of meter over second square, because that is same as the gravity unit. Okay, so in this case, if we want to use b naught and n, we will apply a similar procedure, and that will give us b naught n to the power 5 1 by 4. So if you find the dimension of this one, that will be same as meter per second square, and that is why g is defined as b naught n to the power 5 to power 1 by 4. Okay, so we have defined length scale, that is given here, and then velocity scale, that is given here, and then the g prime scale. Okay, so we have defined these three scales, and now we can actually define dimensionless parameters. Dimensionless parameters, we can define dimensionless radius, which can be given as r to the power hat, and that can be written as r over l. Okay, why? Because r has the dimension of meter and l also has the dimension of meter, and that's why r hat becomes dimensionless. Okay, likewise dimensionless height, let's say that is z hat, that becomes z over l. Okay, and then dimensionless velocity, we can call it w hat, that can be given as w bar by u, and dimensionless reduced gravity, let's call it g hat, that can be given as over capital G. Okay, and you already know what all these different parameters are. So r is the radius of the plume, z is the vertical axis, w bar is the mean vertical velocity, and g prime bar is the mean reduced gravity at any location z. Okay, so w bar, and here we are talking about radius, so I think I need to use capital R so that we are not confused. Okay, so w bar is also a function of z, r is also a function of z, and g prime bar is also a function of z, right? This is something we already know, and that is why your r hat should be a function of z hat, w hat will be a function of z hat, and g hat will be a function of z hat. Okay, so what we have done so far, we have simply converted the dimensional model into a non-dimensional model, or parameters into non-dimensional parameters. So what we can do, or what we will do in the next step, is we will replace the dimensional equation which are given here into non-dimensional equation. Okay, so let's start with this equation. Okay, here you can write Z as L, R square can be written as R hat square L square, and W bar will be W hat U must be equal to 2A W hat and U, and the other side R should be R hat to L. Okay, and here you can see that all these capital terms can be taken out. So this becomes L square U over L. This becomes D by this hat of R square. This, and then UL W hat R hat. All right, and what do you see here is this cancels out. So basically we are left with LU, and that will cancel out with this term. So what do you get here is D by dz hat R square is 2A. Okay, so this is the dimensionless equation where A is already a dimensionless number, right? So A is already dimensionless, so we don't have to worry about that. Now you can see R hat, W hat, both are dimensionless. So this equation does not have any dimension, right? So same thing we can do for the other two equations. Okay, so if you apply the same procedure, you will end up with D by dz hat square W hat square and R hat square G hat. Okay, so this is the equation you will get if you just simply repeat the process as we have followed so far. All right, and then the final equation we have is this equation, that is the buoyancy flux equation, and that also we will copy here. Okay, so this equation will also simply convert into Z hat R hat square W hat G hat will be equal to R hat square W hat, and in this case you will not see N because N will simply cancel out. Okay, so this is the final equation you will get. So now you see there are three different equations. Let's name them as A hat, B hat and C hat. Okay, three dimensionless equations which we need to solve for three different dimensionless parameters, that is the radius, then W and G prime hat. Okay, and in this case we have one constant, that is A, that is a dimensionless constant, and that value can only be found through experiment, and that is why this equation will be solved numerically, but value of A will be taken from experiment.